recording is to discuss tutorial question chapter 3, the remainder of the question 5, question 6, and question 7. So question 1 and 2 is your homework. You have to do it by yourself. Question 3 and 4 I've already discussed in our previous class. We touched on the stoichiometric table for batch reactor. And question 5, 6, 7 is on stoichiometric table for flow reactors, right? So I'm going to discuss slowly. And as I told you previously, for reaction, it's very important to actually understand the question first. Okay, so let us go to the question. The liquid phase reaction in a flow reactor at 150 Celsius. So from now on, okay, when you see the word phase, temperature, the types of reactor, it's very important for you to already take note of this. So the first thing we take note, this is liquid phase reaction. We take note it is a flow reactor, and we take note is 150 Celsius. Right. So the reaction is 1A reacting with 2B to produce 2C. Okay. And given the question certainly says the initial concentration of A and B are 1.8 mole per dm cube and 5.4 mole per dm cube respectively. So from now on, you already know that the first information 1.8 will be your CA naught 1.8 and 5.4 will be your CB naught. Okay, so you already know initial concentration of A 1.8, initial concentration of B 5 CB naught 5.4, and I already taught you if you know the initial amount of your reactant, automatically you can already calculate one important parameter, which is your theta B. So you know that theta B is defined as the initial amount of B over initial amount of A, right? So theta B can be equals to CB naught per CA naught. So you will get 5.4 divided by 1.8, you will get equals to 3. Okay, so as I always tell you, if you know the initial amount, regardless concentration ke, regardless mole fraction ke, regardless molar flow rate ke, if regardless number of moles, if you know the initial amount, you can already calculate the theta B information. And if you have inert, you can calculate in theta I as well. But in this question, they do not mention anything regarding any kind of compound, any kind of inert. So you don't have to calculate theta I, and inert will not be in your stoichiometric table as well. And then they say initial rate of 10 dm cube per minute. Okay, so from now on, you already have to already know to identify what are the values by its unit. So dm cube per minute, dm cube is volume, minute is time, volume per time, volumetric flow rate. And they say initial. So this is initial volumetric flow rate. So it is epsilon naught. So epsilon naught is 10 dm cube per minute. So epsilon naught 10 dm cube. Okay, so this is given specific reaction rate constant of 1.7 at 100 Celsius. So we already know, right? Value of K is very specific to your reaction temperature. So although they give you the K, but this is K at 100 Celsius. So your K 100 is 1.7. Take note, our reaction is at 150 Celsius. So the concept is if you have the value of K, you have to make sure the value of K that you will use in your calculation must be at 150. If you are given any value of K at any other temperature, you have to find the new K at your reaction temperature, right? So they give you subsequently, activation energy 5 kilocalorie per mole. So that's why they give you EA. Activation energy is EA. So if they give you K at 100 and they give you EA, so it gives you an indicator that it means that you most likely have to find K at the new temperature. So what is this new temperature? It's at your reaction temperature. And subsequently, the reaction obeys elementary rate law. So what does this information say? So remember, rate law, we have elementary, non-elementary rate law. So non-elementary rate law, the reaction order of the reactants will be given to you. Okay, so for example, they will say the reaction is first order with respect to A, first order with respect to B. So minus RA equals to KCA CB. So if it's elementary rate law, the reaction orders follows the stoichiometric coefficient directly. So meaning in this case, the stoichiometric coefficient for A is 1, the stoichiometric coefficient of B is 2. So the reaction is first order with respect to A, second order with respect to B. So minus RA equals to KCA CB power of 2. Okay, so that's how you elucidate the rate law. Right. Okay, so we go to the question now. So the question first says, construct a stoichiometric table for the reaction. Okay, all values should be in the function of conversion only by numerically evaluating all other symbols. Okay, so now they ask us to do the stoichiometric table. So I always remind you, before you start the stoichiometric table, you have to first determine, is it a flow reactor or batch reactor? Because if it's a batch reactor, it must be in terms of number of moles. If it's flow reactor, it will be in terms of molar flow rate. Okay, so in this question, if it's a flow reactor, they do not tell us CSTR or PFR, but it doesn't matter. Either way, both are flow reactor. So it means that it tells us our stoichiometric table must be in terms of molar flow rate, or in more specific, FA naught, initial molar flow rate of A. Meaning if you don't have FA naught, you cannot start doing the table, right? So from the information that we are given only these three, right? CA naught, CB naught, epsilon naught. Okay, so you know that epsilon naught, epsilon naught, FA naught, CA naught is related by an equation of which we know that CA naught equals to FA naught over epsilon naught. Therefore, FA naught equals to CA naught multiplied with epsilon naught. Okay, let's say you're not too sure whether this divide is multiplication. You just do unit cancellation. If you have the correct formula, you do the cancellation, you will get the correct unit. So for example, you know FA naught, their molar flow rate. So the unit must be mole per time. We have already calculated theta B previously. You can now do the stoichiometric table. So you remember stoichiometric table for flow system exactly the same like batch system, except that in batch we have to use NA naught, and then the rest you have to follow the formula. So for flow system instead we use FA naught, tetapi formula dia semua masih sama. Okay, contohnya, okay. In this example, we have only three species, okay, A, B, and C, and then the initial, we have change, we have remaining. Okay, so the initial FA naught 18 as we have calculated. Change will be minus FA naught X, so therefore minus 18X. Remember the X is left as it is because we do not know yet the value of the conversion. So remaining will be FA, okay, equals to, you just pick the initial, you copy the initial, you copy the remaining, become 18 minus 18X. So for case of B, so we got FB naught. So FB naught, the formula equals to theta B FA naught. So theta B, we have calculated 3. So FA naught was 18. So you get 54. And then for the change, because B is a reactant, remember, kalau reactant, the change has to be a negative in front of it. Kalau product, the change will be a positive because product will be the number of the molar flow rate of your product will increase because they are produced. The molar flow rate of your reactant will decrease because they are consumed. Okay, so become minus B per A FA naught X. So B per A, please check your stoichiometric coefficient. So B per A will be 2 over 1. So 2 times with 18, you get minus 36X. Then you get your FB, you copy your initial, you copy your change, you get your remaining. And for your C, okay, of course, the initially FC naught is 0 because it's a product. Initially, they are not produced. And then the change, so the change will be plus C per A FA naught X. So C per A, again check, C per A will be 2 over 1. It's the ratio of the stoichiometric coefficient. So times with 18 FA naught, you get plus 36X, therefore FC 36X. Then you have to calculate the total initial. So total initial, 18 plus 54, you get 72. And then the total remaining, FT, you just add the total initial, which is 72, and you can also, and you add the total change. So minus 18X, minus 36S, plus 36X, you will get minus 18X. So the total remaining 72 minus 18X. So we are done for your stoichiometric table. You can see it's very straightforward. It's not that difficult to do the stoichiometric table. Right, so we go to the next question, okay, which is quite similar to the previous one. When we do the batch one, determine the rate of disappearance of A if the conversion is given as 80%. So rate of disappearance of A lagi senang lah kan? Dia nak kita terus cari minus RA. So again, kalau nak cari minus RA, kita kena ingat rate law dia. You have to do the rate law first. Ingat, whenever you want to find any rate, it have to come out from the rate law. So happen case ni terus cari minus RA. So kita kena come out with the rate law first. So the rate law equals to minus RA equals to first K. So K tu kan, as we have discussed extensively, it must be at your reaction temperature. So in our case, the reaction temperature is 150. Suhu reaktor kita 150. Okay, so K kita must be at 150. Then, what about the reaction order for A and B? Sebab tu dia kata, this is follows elementary rate law. Kalau obeys elementary rate law, reaction order dia follows the stoichiometric coefficient. So it's first order with respect to A and second order with respect to B. So it become KCA power of 1 technically, but we tak tulis satu pun tak apa, we understood. CB power of 2 because it's second order with respect to B and first order with respect to A. Right, so first thing first, we have to then calculate lah kan. So K at 150. So you remember, although we're given the value of K, but the K is at 100. So again means that if I have K at any other temperature, I have to find the K at 150 Celsius. So we use the formula K2 equals to K1 exponential EA per R 1 per T1 minus 1 per T2. Okay, and because our R value is in Kelvin, our temperature, which was in Celsius, have to be converted into Kelvin. So you add 273.15. And don't forget, because the activation energy is in kilocalorie per mole, I think it's 5 kilocalorie per mole. But because our value of R is 1.987 calorie per mole Kelvin. So kilocalorie kena tukar kepada Kelvin, you times 1000, right? So you calculate the new K, you will get 3.7714. So the rule of thumb, K must increase with temperature. So the new K you calculate, it must be higher than the one at 100 Celsius. So at 100 Celsius, K is 1.7. So at 150, K 3.77, it makes sense. So most likely your answer is correct. Then kita kena cari pula CA, CB. So to cari CA, okay, so CA kalau batch, CA equals to NA, number moles of A over volume. Kalau flow, concentration of A, CA sama dengan molar flow rate of A yang remaining over volumetric flow rate. To be exact, outlet volumetric flow rate. Okay, tetapi dalam case liquid phase flow reactor, I already taught you, untuk liquid phase, outlet inlet volumetric flow rate ni adalah sama. Hal laju isi padu cecair yang masuk dan keluar reaktor adalah sama. Okay, so that's why we can replace the epsilon, the outlet volumetric flow rate, with 10, which is the initial one. Sebab dalam kes liquid tak ada perubahan isi padu. Okay, so what about FA? How do you get the FA? You just look at the stoichiometric table. FA is equal 18 minus 18x. So I replace 18 minus 18x. My x is 0.8. Then I will get my CA, and subsequently I do the same for CB. So FB, again, I look at my table, I get the value of my FB, I divide by the outlet volumetric flow rate, which is equal to the inlet volumetric flow rate. I get 2.52. I replace CA, I replace CB, but don't forget power of 2 because this is second order. You get your minus RA 8.6220. So this example is very straightforward, very simple. Okay, so that's it for question number 5. Our tutorial, right? So let me read the question. The following is the gas phase pyrolysis of reactant A and B to produce C. Okay, so the key key points that you have to take from this sentence is that this is gas phase reactions. Remember I told you when it comes to chapter 3 onwards, the phase are very important. So you have to really establish from the very beginning the phase of your reactant during the reaction. So in this case, this is gas phase pyrolysis. Okay, so this is the reaction is between 1A reacting with 2B to produce 1C. Right. So the irreversible reaction occurs isobarically and isothermally. So now you know that the concept of isobaric, isothermal. So isobaric means constant pressure, P equals to P naught. Isothermal means the temperature is constant during the reaction. So T equals to T naught. And it's a flow system. So keep in mind this is flow gas system, okay, flow with gas reactant. So you can see later on why this is significant in our answer for the tutorial. And they says with 80 mole percent A and the remainder reactant B. So initially we have A and B, of which 80% of A and remainder 20% of B. So this is mole fraction. So you have YA not 0.8. So hence YB naught is 0.2. So remember that if you have initial amount, regardless concentration, mole fraction, you can use this to calculate your theta B. Okay, sebab we have initial fraction of A, initial fraction of B, we can calculate the theta B. So theta B will be YB naught over YA naught. So 0.2 divided by 0.8, you get 0.25. Okay, so done. From the very first sentence of the question, we already get the first information that we can synthesize. It was determined that the reaction is second order with respect to A and zero order with respect to B. So meaning that they give you information about the rate law, of which is second order with respect to A, but zero order with respect to B. So we can say that the rate law will be, okay, let me go down. The rate law will be minus RA equals to KCA power of 2 because second order with respect to A and zero order with respect to B. So CB power 0 is 1. That's why we don't write anymore, right? So when they give you information about the rate law, it means that this is non-elementary rate law. That's why they have to give you information about the reaction order. Right. So next one, they say the total feed rate of A is 108 million gram yearly. Okay, so this is something new for you. You have not tried to solve this kind of question. Okay, so the question says that they give you feed rate of A, means how much A is fed initially, but the value is million gram per year. So you know gram is mass, year is time. So basically they give you mass per time. So mass per time is mass flow rate. So although they give information about A, but it's in the form of mass flow rate of A. Or normally mass flow rate, we will use M. Kalau molar flow rate F, mass flow rate normally we will use M. So because this is mass flow rate of A initially, so we can put it in symbol as MA naught equals to 108 million. So million is 10 power of 6 gram per year. Because they say gram yearly, that means every year I will use 108 million gram of E. So MA naught 108 gram, a million gram per year. Right. So next, the information given next. So they says initial volumetric flow rate 5 dm cube per minute. So you know this is epsilon naught. Okay, bear in mind for gas phase flow system, volumetric flow rate inlet outlet is no longer equal. So you must really determine is this initial epsilon naught or the final epsilon. So in this case, they say initial. So this epsilon naught 5 dm cube per minute. They give you a specific reaction rate constant, K, 3. So in this case, although they give us the value of K, they do not tell you at what temperature. In this case, it's safe that you can assume it is at your reaction temperature. Okay, again, I repeat, if they do not tell you specifically this value of K at what temperature, you can safely assume it will be at your reaction temperature. Or in other words, you don't have to find any new K. You assume that you can already use that value of K. Okay, so next. They give you molecular weight of A, MW. So molecular weight, you know, right? Molecular weight, the unit is always gram per mole. So they give you molecular weight, 30 gram per mole. And then they say, assume the plant operates 20 hours daily for 300 days annually. So imagine my plant, although we have a year of 365 days, they only operate for 300 days. And for every day, they just operate for 20 hours. Okay, so we will see later on why is this information important. Okay, so let us go to the very first question. Determine the initial molar flow rate of A in mole per minute. Okay, so they want us to know initial molar flow rate, mole per minute. So you know mole per minute is molar flow rate. So they want A, molar flow rate of A initially. So they want FA naught. Okay, so you know that now they want FA naught and your FA naught must be in mole per minute. So now you have to think, how am I supposed to get molar flow rate when the only information that might be relevant is my mass flow rate of A. So I have MA naught, but the question want FA naught. So you have to remember, when we have mass, we want to convert to mole, we can use the molecular weight. Molecular weight is one conversion factor that we can use to convert either from mass to mole, like in this question, or similarly mole to mass. So in this part, it's actually from mass flow rate. So that 108 million gram per year, they want to convert to mole per minute. So we have to make sure all the unit will be consistent. Okay, so first of all, if you remember, to convert from mass to mole, you have to divide by the molecular weight. So let's say you are not sure, should I divide or multiply with the molecular weight? You can always do unit cancellation. What do I mean? Initially, we will begin with what we want to convert, which is our MA naught, 108 million gram per year. So remember, our final target unit must be mole per minute. So I convert first gram to mole. So to convert gram to mole, I will divide by molecular weight. 30 gram at the bottom, mole at the top. So I will divide. So why I do this? Because you can see I will cancel my gram. I'm left with mole. So correct, because my final unit must be mole per minute, mole per time. So I already get the correct mole at the top. So meaning that I must divide with the molecular weight. Okay, so now I already get the mole. Now the challenge is year, because I want my FA naught to be in minute. I must convert from year to minute. So to convert year to minute, you have to be careful with the limitation given by the question, because the question says for every 1 year, the plant only operate 300 days. Okay, you cannot put 365 days because my plant only operate for every 1 year, 300 days. Subsequently, I still want in minute, right? So I haven't reached yet. I'm still at day. I want to go to minute. And then the plant also says another limitation. For every 1 day, the plant only operates 20 hours. So it means for every 1 day, it only operates 20 hours. Okay, so I use it as a conversion factor. So now I'm left with mole per hour. Okay, so the last one, I will convert from hour to minute. So of course, hour to minute, you cannot, you can convert naturally. So 1 hour is 60 minutes. Ultimately, you will get your FA naught as 10 mole per minute. So that is what the answer requires you. Okay, so you get ready the 10 mole per minute for your FA naught. Okay, so that's for part E. So let us go to part B. The part B says, develop a stoichiometric table in mole per minute. All values should be in function of conversion only by numerically evaluating all symbols. So again, they want us to do the stoichiometric table. So remember, as I told you before, once you have FA naught, okay, and you want to do for flow system, you can already complete it. So the challenge is always to get FA naught first. If you don't get FA naught, you cannot start with the stoichiometric table. Once you got it, you can do and complete the stoichiometric table. So in this one, I'm not going to elaborate long because the formulas are all the same, except that instead of using an A naught, I will use F A naught. Okay, so let me go to the next question. So that question says, determine the rate of formation of P if given the conversion 40%. Okay, so now dia nak cari apa? They want you to find, again, rate of formation, positive R. Kalau rate of disappearance, negative R. This is rate of formation, positive R. And they want for compound B, positive RB. Okay, so they want to find positive RB. However, if you remember, I already taught you many times, whenever you want to find the rate of disappearance or formation of any other compound, you have to first find minus RE. Okay, because the rate law is based on minus RE. So you have to find first minus RE, then only you can find the rate of other formation. So you may ask, how does it related? So it's related by this equation that which I have taught you before. So the correlation is positive RB equals to, again, remember the number can be positive or negative depending on the role of the species during the reaction. So for example, in this case, they want rate of formation of B. Okay, when you check the chemical equation, B is a reactant. I want to find rate of formation, but B disappear. B does not form. They don't agree to one another. The number will be a negative number. So don't forget about that. Negative positive of the number is solely determined by what you want to find and the role of the compound in the reaction. If they agree to one another, they are positive. If they don't agree to one another, the number is negative. Then multiply with the stoichiometric coefficient of B over A. So from the reaction is 1A reacting with 2B. That's why B per A become 2 over 1. Multiply with minus RE. So remember I told you that's why we have to find first minus RE. Okay, so let's we go. How do we find minus RE? So minus RE just now from the question above I have discussed the rate law is given as second order with respect to A, zero order with respect to B. So minus RA equals to KCA power of 2. Okay, CB power of 0 is 1. We don't write it anymore. So first, K, we can already use the K because they do not say the K at what temperature. We can assume it's at our reaction temperature. We straight away can use the value. Okay, now we find CA. So CA now becomes the challenge because if you remember, CA is no longer straightforward for us to find, right? Because although the first part is the same, CA equals to FA over epsilon outlet volumetric flow rate. Okay, so FA part you don't have to worry, but FA we can see from your table. Table they give us FA is 10 minus 10x. So the x I can replace with 0.4. So the up is okay. Now the problem is epsilon. So because you remember, the formula says that epsilon outlet volumetric flow rate equals to initial volumetric flow rate epsilon naught 1 plus epsilon x. Technically, you have P naught per P, T per T naught. But because they say this is isobaric isothermal, so the P naught per P, the T per T naught is no longer there, but they're equal to one another. So now it becomes outlet volumetric flow rate epsilon equals to epsilon naught 1 plus epsilon x. Okay, so that's why we write it as like this. Okay, so you can do one way is you can first find, you can replace first epsilon naught, you can replace the epsilon and the x. Mean you calculate first the outlet volumetric flow rate, then you substitute inside. Okay, so let us do that. Okay, so epsilon outlet volumetric flow rate equals to initial volumetric flow rate. So given in the question, initial volumetric flow rate is 5 dm cube per minute. So tu masalah dia, kalau liquid, outlet inlet volumetric flow rate is equal. That's why you terus guna. Tapi untuk gas phase, dia dah tak sama. Sebab outlet equals to inlet in bracket 1 plus epsilon x, P naught per P, T per T naught. Tapi P naught per P tu dah tak ada sebab isobaric. T per T naught pun tak ada sebab isothermal. Okay, so I replace inside. So next, in bracket 1, okay, dia punya formula plus epsilon. So you have to calculate epsilon first. So dia bukan epsilon, epsilon. So epsilon nak follow formula dia, kamu kena cari dulu. And the epsilon a bit difficulty sebab dia ada formula dalam formula. Okay, so you have to find one by one. So epsilon formula dia given as equals to YA naught sigma. You don't have to memorize this, okay? It's given to you, but you have to know how to use it, right? So equals to YA naught sigma. YA naught ni kamu tahulah kan, initial mole fraction of A. So kalau dalam soalan ni, initial mole fraction of A is 80% mole A. So let me go up. 80 mole percent A initially. So YA naught tu 0.8, 0.8 done. Sigma is something that you have to find. Okay, sigma dia tak ada fixed formula. So you have to remember dia adalah to calculate the ratio of the stoichiometric coefficient, which it will be positive for product but negative for reactant. So in our case here, the reaction is 1A, 2B, 1C. Okay, so it becomes product is only one, right? C, right? So it becomes C per A positive because C is a product, minus B per A because B is a reactant, minus 1 or technically is A per A. Tapi A per A itu satu. Saya kata tolak satu. So that's why it become YA not 0.8. In bracket, C per A is 1 over 1. Sebab 1A react with 2B to produce 1C. Minus 2 per 1 because 2B minus another 1. Minus 1 from the A per A. So you multiply this, you get your epsilon negative 1.6. Okay, so when you get epsilon, you can replace into the equations. But equation dia 1 plus epsilon x. But because my epsilon is negative, so become 1 minus epsilon x. So it's replaced over here that I'm trying to highlight here. So then now you replace with the x of 0.4. So you replace with the conversion, you get your CA. When you get your CA, okay, you come back, you replace into the minus RA. Just now kita dah ada K. Now you can replace the CA with 3.333. So you get your minus RA, 33.3327. You replace into the positive RB. Okay, remember, if we want to find positive RB, you still only get minus RA. We want to find positive RB. Okay, right? So you replace into the final equation. Finally, you get your positive RB as negative 66.6654. Okay, so this is the solution for question number 6. Right, thank you. Tutorial chapter 3, question number 7. So the question says, ethane gas at 75 mole % and the remainder nitrogen gas enters the flow reactor at the rate of 10 dm³ per minute at the total pressure of 5 atm and a temperature of 1000 Kelvin. Okay, so in this one sentence, you can see we have a lot of information that we have to process. Okay, so first of all, this is initially I have the mole fraction of ethane. So in my reaction, I'm using ethane. So I have my A, which is my YA0 is 0.75. However, although my reactor is only ethane, but my initial inlet not only consists of ethane, but I also have nitrogen gas, which is my inert. Okay, so again, although I may have one reactant, however, not necessarily it means that initially in my reactor is only my reactant. It may have the inert that flows together. So in my case here, I have YA0 0.75, my ethane, and my inert, which is my nitrogen gas, YI0 will be 0.25, right? Because it's 100%. So YA0 0.75, YI0 0.25, and subsequently, when you have these two value, you can calculate the theta inert. So remember, if I have initial amount of B, initial amount of A, I can calculate theta B. If I have initial amount of inert and I have initial amount of A, I can calculate theta I. So I got my theta I as YI0 over YA0. So it's 0.25 divided by 0.75. I get 0.33. So done. I already get my theta I. Okay, so next, dia kata, enters at the rate of 10 dm³ per minute. So dm³ is volume, minute is time. So volume per time is volumetric flow rate, and this is initial volumetric flow rate. Epsilon naught is 10 dm³ per minute. Okay, so again, kalau is gas phase, you have to be very careful and check whether it is initial volumetric flow rate or final volumetric flow rate. Okay, so this is epsilon naught. This is total pressure 5 atm initially. So P0 is 5 atm. Temperature 1000 Kelvin. T0 is 1000 Kelvin. And they say isothermal isobaric. So T equals to T0. P equals to P0. Okay, so means there's no changes in pressure and temperature, right? So this is stated in this red color font, right? So then, so let us go to the question. Construct a stoichiometric table for the reaction. Okay, all values should be in function of X only by numerically evaluating all other symbols. So in this case, you have to do the stoichiometric table. So again, follow the concept. Stoichiometric table, flow reactor, dia mesti ada F FA0. If you don't have FA0, you cannot do the table. Okay, so in this question, we were not given FA0. However, this is gas phase. If you have temperature, you have pressure of a gas phase, you can calculate the CA0 ready because we have epsilon naught. I have epsilon naught, I have CA0, I can definitely get my FA0. And if it's a gas phase, I can use the either gas law to get CA0 first. So in this question, they give us P0 of 5 atm. They give us YA0 0.75. They give us temperature 1000 Kelvin. Okay, so you can find the CA0 as 0.05. So it will be mole per dm cube. So let me put the unit here. So CA0 0.046 mole per dm cube. Therefore, I can use it to find my FA0. So FA0 equals to CA0 multiplied with epsilon naught. So again, if you forget, is it multiply or divide? You do unit cancellation. If you get the final unit, which is in mole per time, then most likely your formula is correct. But if you don't get the unit that you want, then you have to recheck back. Okay, so after you get FA0, naturally you can start doing the table. But you have to be very careful in this question, right? The reaction is 1A to produce 1B and 1C. And you have one inert, which is nitrogen gas. So you have 4 compounds in your stoichiometric table. Okay, so you have C2H6, C2H4, your product, H2, your product, and N2, the inert. Okay, so the table is quite the same except for the case of B. So B is a bit unique because remember, B in this case is product. So initially, B will not have any FB0 because B is a product. Okay, the change for B will be a positive one because B will be produced. And subsequently, similar to the case, inert as well. So previously, we don't have inert, but in this question, we have inert. So you have to calculate Fi0, you have to calculate for the remaining for your inert as well. So this is slightly different for this question, of which now my B is a product and I have an inert. So this is something that you have to pay attention because the questions sometimes may differ in that sense. So I'm not going to discuss further about the table. Very straightforward. I just highlight the important ones that you have to be careful about. So let us go to the very last part of the question. So the question says, calculate the rate of formation of hydrogen gas at 600 Kelvin for a conversion of ethane of 70%. So again, dia nak apa? Dia nak rate of formation, positive R. Hydrogen gas is our C. So A, B, C. So they want positive RC, at which it must be at 600 Kelvin. So positive RC pada 600 Kelvin. Okay, the activation energy of the reaction is 15 kilojoule per mole. So your EA is 15 kilojoule per mole. Your pre-exponential factor 0.5 per minute. So they give us EA, they give us A. Okay, so how do we do this, right? Okay, so now we come back. If you got confused, you go back to the very first part of the question. Apa yang dia nak? Dia nak kita cari positive RC. So you remember, right? Nak cari rate of other compound, kita mesti ada berkaitan dengan minus RE dulu. So the correlation positive RC equals to, okay, dia adalah hydrogen gas adalah product. Saya nak cari rate of formation. Hydrogen is really being formed. They agree to one another. The number is a positive. So positive multiply with C per A, the stoichiometric coefficient ratio, multiply with minus RE. Okay, so nombor dia positif sebab kadar pembentukan hydrogen memang terbentuk, they agree to one another, the number is a positive. Okay, so now we calculate minus RE first sebab dia kena berkaitan dengan minus RE. Okay, so rate law pula, how do we find the rate law? Okay, so kita nak cari minus RE, right? So minus RE equals to K. So kita tahu K dia mesti pada 600 Kelvin because the reaction is at 600 Kelvin. So that. Reaction order, kita ada concentration, right? Kita kena reaction order. So in this question, they actually don't tell us any information about reaction order. Dia pun tak cakap elementary, non-elementary. Dia pun tak bagi sebarang information. So how do we solve this? So the only information that may be related is actually the value of A. So you may wonder, kenapa pula value of A itu berkaitan? Sebab value of A itu diberi sebagai 0.5 per minute. Unit tu yang penting. Dia bagi minit per minute ataupun dalam dimension per time. Okay, so apa kaitan dia? Jadi kita nak tahu kan sama ada tu first order ke, second order ke, sebab sekarang dia hanya ada reactant A, right? So it's either zero order towards A, Ca power 0 ke, Ca power 1 first order, or Ca power 2 second order. How do we know? Okay, so you check back Arrhenius equation yang kita pernah belajar. We have learned Arrhenius equation. K equals to A exponential minus EA per RT. And I have taught you before that unit A pre-exponential factor akan sama dengan unit K sebab part yang belakang exponential ni unit dia dah dimensionless, dah tak ada unit sebenarnya, unitless. So naturally unit K sama dengan unit A. So kalau unit A per minute ataupun per time, unit K pun per time. So kalau kamu ingat saya ajar kamu dulu, we have already taught you, we can guess the reaction order by looking at the unit of K. Kalau dia satu reactant, kalau unit K dia adalah concentration per time is 0 order, per time first order, 1 per concentration time is second order. If you're not too sure about this, you go to chapter 3, part awal tu saya dah ajar kamu mengenai macam mana kita nak tahu rate law, reaction order by looking at the unit of K. So when you have the unit of A per minute, which means unit K pun per minute, ini to indicate that the reaction is first order with respect to A. Okay, so unit A sama dengan unit K, unit dia per time tu maksudnya dia adalah first order reaction. Therefore, rate law dia minus RA equals to KCA. So that's how you elucidate the rate law. Slightly different from the way that you usually do, but this is how we elucidate the rate law. So now you get ready, minus RA. So kita buatlah, kita cari minus RA dan kita cari positive RC. So nilai K. So masalah nilai K ialah kita tak tahu nilai K. Kita hanya tahu A, EA. Tapi you have learned, right? We can find K if we know A, EA dan temperature. Okay, remember Arrhenius ada dua version. Equation yang selalu kita guna tu adalah bila saya tahu K1, saya nak cari K2. This one is saya nak cari K terus. So I have A, EA, I know temperature, I can find my value of K. Okay, then I will get my K as 0.02472. So K dah settled. Next one nak cari CA. So CA check balik. CA equals to FA over epsilon. Outlet concentration of A ataupun remaining concentration of A equals to remaining molar flow rate of A over outlet volumetric flow rate. So FA senang, tengok sahaja daripada stoichiometric table. FA is 0.46 minus 0.46x. So 0.46 tolak 0.646x. Bottom epsilon, right? So we have to first find epsilon. So again, from the formula, kalau kamu ingat, epsilon equals to this one. Epsilon, outlet volumetric flow rate, epsilon equals to, this is gas phase flow system. Epsilon equals to inlet epsilon, inlet volumetric flow rate, in bracket, 1 plus epsilon x, in bracket, P naught per P, T per T naught. Tetapi this is isobaric isothermal. P naught per P, T per T naught tu dah tak ada. So jadi outlet volumetric flow rate sama dengan inlet volumetric flow rate 1 plus epsilon x. Okay, so kita cari one by one. Okay, so outlet volumetric flow rate equals to inlet volumetric flow rate 10. Okay. Tadi punya soalan, in bracket 1 plus epsilon x. So kita cari dulu epsilon. So epsilon equals to YA naught sigma. Okay, itu formula dia. So YA naught sama dengan 0.75 ethane punya inlet molar, ethane punya initial molar composition, mole percent is 0.75 multiply with sigma. Sigma tu ada formula pula. Sigma tu adalah the ratio of your stoichiometric coefficient. Positive for product, negative for reactant. So reaction ni tadi adalah 1A dengan 1B, 1C. So B and C is product. So B and C akan menjadi positive. So dia menjadi B per A, stoichiometric coefficient of B over A plus ratio of stoichiometric coefficient C per A minus reactant technically E per A. So minus 1. So you can see that you don't have to calculate for inert sebab inert tak ada stoichiometric coefficient. So sigma is only for your reactant and your product. So you multiply, you will get epsilon as 0.75. So that's why it become now inlet outlet volumetric flow rate equals to initial volumetric flow rate 1 plus epsilon 0.75 X. So the outlet multiple rate, you substitute at the bottom, you replace the X with the conversion 0.7. So you get your CA 0.009. So I already have K, I already have CA. I can calculate to get your minus RA, and subsequently you can calculate to get your positive RC. So you can see this question is not so hard, just that there's slightly changes here and there of which you have to really understand. So that's all for tutorial chapter 3. So I'm done with the tutorial. Okay, thank you.